Hi there, thanks for joining us for this fourth installment of lecture videos for chapter 2. Sorry, the last one was a little bit long. I think we'll be short on this one. So we finished talking about different types of reaction mechanisms you might see, whether it's dissociation, coordination, substitution, addition, or acid-base type of a reaction. And in that case, how do you know which way the reaction might go towards, which species is more stable? Well, the reaction equation would lean toward the side that has a more stable species. So you can tell that by applying the carry rules, right? And all that reaction that happens in organic chemistry kind of depends on what we call functional groups. The functional groups is where the reaction takes place. Okay, so for that reason, it's super important that you know what the functional groups are. And then I kind of apologize that in this introductory chapter, you tend to have to kind of memorize a lot of things because it's all kind of new stuff to you. But hopefully you've had some exposure to functional groups, even in general chemistry or prior chemistry classes. So without further ado, let's just get through the different classes. And for this, as much as I hate to ask you to memorize things, because that's not the best way to learn organic chemistry is memorization. It's usually the best way is to reason through things, problem solving. But this sort of fundamental sort of vocabulary stuff, I don't see how you can avoid just memorizing. So please do memorize these 2 pages of notes. It's really important. And it's not just memorization, though. You do have to be able to identify these different types of functional groups in a complex molecule, and I'm sure we'll practice that during class time. So what are different functional groups? Well, functional groups are the groups of atoms or groups of atoms that sort of define the reactivity of the molecule. And hydrocarbons are arguably the most boring one. They're very nonpolar. Just like the name suggests, it's just made of hydrogens and carbons, which are pretty similar in electronegativity. That means there's no polarity in the molecule, and hence if there's no polarity of electrons in the molecule, you can imagine that reactivity is really low. It just really doesn't do anything. The worst of all, or most boring or most stable of all, might be the alkanes. That look like this, right? I guess we don't need to make it plural. Whereas alkene has double bond in it, but it's still hydrocarbons, hydrogens and carbons. Alkyne with a Y, notice those are the only difference, A, E, or Y. Has a triple bond in it, and by necessity it's sp hybridized, and so for that reason I hope it makes sense to you that the bond angle should be 180 degrees, and for that reason it's kind of awkward to draw this as a zigzag. In fact, that would be kind of wrong. It's a 180-degree bond angle right here at these 2 carbons. Hope that makes sense. And another might be aromatics, or sometimes we might call these arenes or aryl groups. The most famous example might be benzene. Okay, so this basically is like alkenes, except they're in a ring and conjugated, meaning they're all next to each other, and we'll talk about why that matters in a separate chapter later in the year. And another class of functional groups are made of polar, or contain polar single bonds. The easiest one, the first ones we would encounter with haloalkanes. And that's what it sounds like. It's just alkanes with a halogen group in it. Or sometimes I might say alkyl halides. Kind of mean the same thing. The latter name emphasizes the fact that the halogen can leave as a negatively charged anion. Or, of course, instead of chlorine, that would be an example. But instead of chlorine, you could have fluorine, of course, chlorine, or bromine, or iodine. Those are the main examples here when we say halogens. Okay. Another example of polar single bonds, and of course here's the polar bond. Polar single, another example would be an alcohol. In organic chemistry, when we say a alcohol, we don't necessarily mean the alcohol that you can drink. That is one of the, that's a molecule that has an alcohol functional group. So here's a non-drinkable alcohol, like you would die if you did, but this has an alcohol functional group. It just means it has an OH group attached to a carbon. That's an alcohol. Okay. Similar one would be ether. Ether is when you have, just like alcohol, you have this oxygen-carbon bond, but you have that on both sides, right? So there's no hydrogen attached to the oxygen. So for that reason, it's actually much less reactive, because this is a very polar bond, OH bond, so it's very reactive right there. Another kind of variation of this is what we call thiol. Thiol is just the old word for sulfur, so here's an example of that. Instead of OH functional group, we have an SH, and hopefully this makes sense to you. Oxygen and sulfur, they're in the same family or column in the periodic table, so they have a similar reactivity profile, but thiol is sort of the sulfur version of alcohol, and it's quite different than alcohol, but we'll talk about that. Acetal is another example, so that's sort of a special version of ether in a way, but here's an example of an acetal. Right, because it's got the two oxygens on one carbon, or two, I should say two ethers and one carbon. And that makes it a different reactivity profile than ether, for example. It's more reactive than ether. There's a thing called hemiacetal. So obviously it's related to acetal, and the difference is one carbon has two oxygens, just like acetal, but one side is not ether but an OH group. Okay, so it's kind of like halfway to becoming acetal. That's called hemiacetal. Hemi means half. The last example that's quite distinct from the rest is an amine. Could come in different flavors. This would be called primary amine when the nitrogen only has one carbon on it. Here's a secondary amine. If the amine has three carbons on it, or alkyl groups, this would be a tertiary amine. Okay. Likewise, when the carbon that bears the alcohol is attached to two other carbons, that's called secondary alcohol. So this is technically a secondary alcohol. Now, there's functional groups that have a polar pi bond, in other words, double bonds, and those are, here's some examples. There's that polar pi bond, carbon-oxygen double bond. This is called an aldehyde. And it might look very similar, but this is called a ketone. Okay. And this is called a carboxylic acid. Maybe I'll move that over a bit. And as you can imagine, the reason why this is called an acid is because this proton here is fairly acidic. It has the pK of around 4 or 5. And one more similar one. If instead of having OH on the same carbon as carbon-oxygen double bond, if you have basically like an ether bond, that's called an ester. Okay. Now, these are all have something in common, in that this carbon-oxygen double bond, right? These are all called the carbonyl group. Sometimes students make this mistake of calling everything that has a carbonyl group a ketone, but it's not. This is not a ketone. Ketone has to have a carbonyl that's flanked by 2 carbons. Aldehyde has a carbonyl that's flanked by a carbon, but then it has a hydrogen on it, so that makes it quite different. Carboxylic acid, would have a carbonyl group and an OH group on the same carbon. Ester has carbonyl and essentially like an ether group on the same carbon. Okay, so that's the difference, and hopefully the goal is you need to be able to identify these functional groups in a complex molecule, bigger molecule. Okay, here's another carbonyl compound example. It's an amide. It's kind of like the amine version of ester, okay? And this can come in different varieties. This would be considered a secondary amide because the nitrogen has 2 carbons on it, whereas like if you have something like this, that would be a primary amide, whereas this would be, you might have guessed it, a tertiary amide. Okay. And then the last polar pi bond functional group we might cover for now is a nitrile. You may have known this as a cyanide group, but when it's part of a organic molecule, we tend to call those a nitrile group. Okay. So those are the functional groups I want you to know and be able to identify in a larger molecule, which I'm sure we'll practice in class. But the reason why you need to know and be able to identify these functional groups is they react differently. One of the reactivities that we repeatedly see in organic chemistry is acid-base reactions, like we talked about in the last video. So it might be good to point out, and it would be good for you to sort of know the range of typical pKa values for typical functional groups. And again, I hate to ask you to memorize something, but this would be, if you do remember this will really help you. It's not gonna, this is the kind of information that, like, if you have to look it up every time, you're not gonna be able to use that information effectively to judge or evaluate a complex reaction mechanism later. So you just kind of have to know. I get the temptation to think, in this digital day and age, if it's something you could like look up by Googling, why do I have to memorize? It's because you want to be able to think through larger concepts, bigger ideas later down the road. Okay. So let's compare some pKa's of functional groups. The worst acid, or the highest pKa would be something like this. You can't really pull this proton off of alkane much at all. Carbon is not very electronegative, so if you think about the conjugate base of this, where you're left with a negative charge in carbon doesn't know what to do with it. It's very unstable, so for that reason, this is one of the worst acids there is. Not as bad as that, but it's still a pretty bad acid, would be an amine. And you might think, well, isn't that a decent base? Well, it is, but it's a horrible acid. And what we mean by that is it's hard to pull off one of these protons off of amine to make an amide anion. And you might get confused because you might be thinking, isn't amide this neutral functional group? Unfortunately, in the history of organic chemistry, I don't know why, but the conjugate acid of amines are also called amide anion. Excuse me. Oof. And that's just kind of a coincidence in a way that that's also called amide. And I don't know why I'm apologizing because I didn't come up with this name, but that's just kind of the way it is. And amide anion is very strong base, okay? And so for that reason, this is a fairly bad acid, strong base, bad acid, okay? Now, the next one up would be, we're kind of going from worst to better, best, okay? Would be this hydrogen. You might think, well, that's like a pretty bad acid because it's on a carbon, but remember the hybridization matters a lot, so that's the A rule in the carry rules, if you recall. And so for that reason, this is much more decent of an acid than alkane, and this would have a pK of around 25. Okay, it's still not great, but much better than alkane, even better than amine. And then to contrast all of that, when a proton is on oxygen, as in when it's part of an alcohol, this has a pK of around 16. It's much better acid than any of these we talked about. And at this point, the acidity kind of matters. It's this is low enough pK that it starts to matter as an acid. Okay. What's the next one down the list that we should be aware of? And I don't want you to get confused between amines and this ammonium ion. Or cation. But when we're talking about one of these protons, the behavior is much different. This nitrogen has one too many protons and hence the positive charge, right? So this is a much stronger acid than amine with a pK of around 9. Okay. And we talked about carboxylic acid earlier. Here's a carboxylic acid example. This in particular is acidic, called acetic acid. You might remember the polyatomic ion acetate from Chem. If you put a proton on that, that's acetic acid, and indeed that proton is somewhat acidic, and it has the pK of around 4.7. Okay, and then just to kind of wrap this up, another species we've already encountered is this hydronium ion. Right, and its proton has wants to leave pretty badly because it's making this oxygen positively charged, and that's very uncomfortable for oxygen, which is very electron negative. It wants electrons, and yet it has deficiency of electrons when it's positively charged, right? That means, yeah, it's missing electron density, and so this is uncomfortable. And so for that reason, this is a pretty good, in fact, it's a strong acid with a pK of negative 1.7. Anything that has a pK of below 0 is usually considered a strong acid. And as far as we're concerned in organic chemistry, one of the strongest acids we might consider would be that on a sulfuric acid or a bisulfate ion. Is a bisulfate ion. this is around pK of 9-ish. Oh, sorry, -9. So it's much stronger than hydronium ion, even. Okay, so those are the pKs I want you to be aware of. Yeah, we'll do some practice, I'm sure, of this in the homework and perhaps also in class, I'm sure. So I'll see you then.